Maths educational video. Convergence of infinite series. We have learned the concept of convergence of sequences in the previous video. We are now going to take one step forward and look at convergence of an infinite series corresponding to a sequence. First, let's define a very important term known as the partial sum. Given a sequence an, the partial sum of an is the sum of its first n terms. Sn is itself a sequence because it depends on n. Before we define the concept of convergence, let's look at a familiar example. Geometric series. When we are given a geometric sequence with first term a and common ratio r, we know that the sum of its first n terms is given by this familiar formula. So this is the partial sum for this geometric sequence. And what we want to do now is, treating Sn as a sequence, we want to ask whether Sn will converge to a finite real number when n goes to infinity. So it's about the concept of convergence of a sequence. This time the sequence is the sequence of partial sum. When you let n go to infinity, we are summing the entire sequence. You are summing ak for k from 1 to infinity. So this is known as an infinite series corresponding to the sequence an. Convergence or divergence of this series is defined to be the convergence or divergence of Sn, the sequence of partial sum. Let's consider a few simple examples. In the first example, we are summing k from 1 to infinity. We first compute its partial sum, which is the sum of k from 1 to n. This is a famous algebraic formula. Obviously, when n goes to infinity, this quantity will diverge to infinity. And the reason is simple. That's because both n and n plus 1 diverge to infinity. So our conclusion is that this sequence Sn diverges to infinity, which means correspondingly the infinite series is divergent. We now look at a convergent series. And again, this is a familiar example. We have a geometric series. The first term is equal to 3/4. That can be obtained by letting k equal to 1. Common ratio is 3/4 because of the term here. Partial sum for geometric series we have just seen is given by this expression. And now we want to let n go to infinity. It's obvious that 3/4 power n will go to 0 when n goes to infinity. In fact, we have a more general result given in the box. For any r strictly between -1 and 1, r power n will converge to 0. So the outcome is Sn will converge to 3/4 divided by 1 minus 3/4, which is equal to 3. So the conclusion is that the given infinite series is convergent and converges to the value of 3. Here's just a summary of a result on geometric series. A geometric series with common ratio r will converge if and only if r lies strictly between -1 and 1. And the value of the series is given by this familiar expression a divided by 1 minus r. We end the video with an example on geometric series. It's not immediately clear that this is a geometric series, but if we keep in mind that a geometric series will always take this form, then all we have to do is to try to express the given sequence in this form. And we'll do some algebra. First of all, 100 is a constant, so we focus on those with a k. We have x power k in the numerator, 5 power 2k minus 1 in the denominator. So obviously we do some algebra. We will split 5 power 2k minus 1 into a form that looks like this. Because this is exactly the exponential form that we need. So applying the integers law, 5 power 2k can be written as 25 power k. 5 power minus 1, we can write it out separately as a constant. So now you can combine these two constants to get 500. And we can combine these two exponential terms into a single term. Doing so allows us to get the common ratio for this geometric series. So R equals to X divided by 25. And following the theorem that we have just seen, the geometric series converges if and only if the common ratio lies between -1 and 1. So we solve this inequality. Multiplying throughout by 25, we get the range of X as desired. And finally, the value of the series is given by the formula A over 1 minus R. But A, the first term, can be found by substituting K to be 1. So that will give us 20X. Applying the formula, we get the sum to infinity.